In our paper, we introduce LOCAL, or Location Calculus. It is an intermediate language for the Gibbon compiler, meant to represent programs that operate directly on serialized data. Here's a simple recursive function that sums the leaves of a binary tree. The in-memory representation you'd expect would be something like this, where the nodes have pointers to their children. When computing the sum of this tree, we need to follow all these pointers, and if we read this tree initially from disk, we would have to deserialize it first to build this. As an optimization, we might want to avoid deserialization with some C code where we compute the sum efficiently by walking through the bytes. No need for building and traversing the pointer-based tree. This is significantly faster, but of course this sort of C code is very tricky to write. Local is a high-level language for doing exactly this. Serialized values are annotated with relative location information. When building the tree, types symbolically track how values are written to memory. Local allows programmers to use pattern matching and recursion to operate directly on serialized data in a type-safe way.
Scenic is a domain-specific probabilistic programming language for describing scenes. Why scenes? Suppose you're designing an autonomous system with complex software inside. Will your system work? To answer that question, you need to define the range of possible environments the system must operate in. Scenic lets you formally define a distribution over environments, which you can then sample to generate data useful for designing and testing your system. For example, if your car-detecting neural network has trouble with overlapping cars, you can write a scenic program describing such scenes, generate many of them, and augment your training set. Or, if the network thinks one car is 3 cars, you can debug. Is it because of the model of the car, or its position, or the background of the image? To learn more about the design of Scenic and how we used it to improve the performance of a state-of-the-art neural network, please come to our talk.
Today, a number of frameworks like TensorFlow and PyTorch allow ML practitioners to run ML models on high-end hardware like Intel CPUs, NVIDIA GPUs, and large FPGAs. These frameworks generate efficient code for the target devices without incurring significant developer effort. However, recently, many compelling applications have emerged which require ML models to be run on tiny IoT devices like Arduinos, ARM Cortex-M0s, and embedded FPGAs. These devices have low resources and no floating point unit. But there are practically no frameworks in this space. To bridge this gap, we have developed CDOT, which is a language and a compiler. Our language allows ML researchers to succinctly express their ML models. Our compiler uses an automatic quantizer to generate efficient fixed point code for IoT devices. For more details, please visit our webpage.